Okay, good afternoon. I want to cover one example problem and then the different models if I can in the time that we have remaining. So, right, there you go. So the BJT has three regions of operation or three modes of operation: cutoff, saturation, and active, right? So let's look at an example. Actually, did we? Oh, we didn't cover this slide. Okay, the two sections are out of sync. All right. So let's back up before we get to the example. Three modes of operation for a BJT are cutoff, saturation, and active. If we use the BJT in cutoff and saturation mode, not at the same time, obviously, but if you use two modes, alternately switching between them, then we can operate the BJT as a digital switch. So in cutoff mode, we say the BJT is off. In saturation mode, we say the BJT is on. Active mode is where we use it as an amplifier. So we can determine the mode of operation by looking at the two junctions, seeing which one is forward bias, which one is reverse bias, and of course, vice versa. If you reverse bias a few junctions in the forward bias or reverse bias, then you know which mode of operation transistor is in. If both junctions are reverse bias, transistor is cut off. This is an NPN transistor. It's two back-to-back PN junctions. So if you forward bias a PN junction, junction is off, junction is on. If you reverse bias the junction is off. So this one right here, where emitter voltage is higher than the base voltage, would mean the N-type material is at a higher potential than the P-type material. So the PN junction is off. Reverse bias, it's off. So this mode results in the transistor being cut off. Okay. On the other hand, if we take both PN junctions and we forward bias those PN junctions, meaning both are on, then the transistor is in saturation. Transistor is in saturation. So, and saturation in this case refers to the fact that the current is at a saturated limit. Okay, it's operating like a current source. So there's a clear pathway, clear and open pathway for the current to flow through the transistor. So again, both junctions reverse bias, it's cut off. Both junctions forward bias, it's in saturation. If one of the junctions is forward bias and the other one is reverse bias, then we say a transistor is in active mode. Which is also the fundamental operating principle behind the transistor. Again, this is the NPN transistor. In this particular mode, the base emitter junction is forward bias. One junction is forward bias. And the other one, the base collector junction, is reverse bias. Okay, and you can see that in the polarity that is shown. The polarity that's shown here has nothing to do with the measurement. It's simply stating which end is higher. Okay, the polarity that's shown here, plus minus signs, are simply showing you which junction is higher with reference to the other one. Okay. So three modes of operation: active mode, saturation, and cutoff. There is also a fourth mode. Remember, I say if I reverse bias one junction and forward bias the other one, right? And that's not shown on here because it's irrelevant or immaterial. If base emitter junction is forward bias, and collector base or base collector junction is reverse bias. Sorry, not, this is the other way around. If collector base junction is forward bias and base emitter junction is reverse bias, it is known as the reverse active mode. Essentially, all it does is it ensures the transistor is off. That's all it means. Okay. The active mode is also known as the forward active mode. And if the collector base junction is forward bias and the base emitter is reverse bias, then it's known as the reverse active. Essentially, the transistor is off. Fundamental question, why? What's so different with these two? That's absolutely correct. So remember, the transistor, the BJT, is not a symmetrical device. The emitter is the most heavily doped. So that's where the majority of the charge carriers are originating. If it's an NPN transistor, the emitter is supplying electrons. If it's a PNP transistor, it is supplying holes. If the base emitter junction is not forward bias, there are no charge carriers that are present. Transistor is completely off. So in general, this also leads me to the important point saying that if you check the base emitter junction the first, and if it is not forward bias, then the transistor is off. And we don't need to check anything else anymore. Again, if the base emitter junction is not forward bias, then there are no charge carriers that are present in large numbers, basically. So we can just state there are no charge carriers present, and the transistor is essentially off. We can also say it's just cut off. That's the only mode of operation that would be valid. Okay. So that's the first check that we perform. Now, if the base emitter junction is forward bias, then it could be either inactive or in saturation. And then we perform two more checks, right? So let's look at that with an example. The reverse active mode is not studied, but it's just something that students must be familiar with. If you're working in a lab, your circuit's connected correctly and it's not working, well, the reason it's not working might possibly be that the terminals are flipped. Again, because it's not you're not going to end up blowing out the transistor. You're simply forward biasing the collector and base, but the collector does not have any free charge carriers. Very limited. It's almost close to an intrinsic semiconductor. Okay, would not have much charge carriers available. So you could apply a very high electric field and it still wouldn't work. All right, common emitter configuration. Emitter is common to the input and the output. This is the input characteristic. This is the output characteristic. We already saw the output characteristic. The input is, of course, a forward bias PN junction. And the output characteristics is a set of data points for every single value of IB. The same way we can have characteristics for PNP, exactly the same. The only difference is that the voltage polarities are reversed or flipped because the electrons are switched with holes. Holes are switched with electrons. So the voltage that is measured, you have a PNP transistor. So the base emitter junction, base is N and emitter is P-type material. So if you forward bias and you still measure VBE, your voltage is going to be minus 0.7, simply because our reference is still the same, right? VBE right here is negative because VEB is positive. Emitter is P-type, base is N-type. Forward biasing means the base is lower than the emitter. So everything remains the same, except it's the second quadrant, not the first. And that's why everything's negative. Other than that, there's no other difference in operation. Current directions are flipped, voltage polarities are flipped. Everything else remains the same. All right, example, try to determine the operating mode. All of the relevant values are given. All we have to do is determine which terminal out of the collector base emitter is a lot higher than the other one. So VCC is given to us 12 volts. VBB is given to us 4 volts. In this case, it doesn't actually matter because the terminal voltages are already provided to us. So we don't need to perform an analysis. We need to observe and simply determine the mode. Okay, analysis, sorry. We need to observe and analyze, but we don't need to calculate. Okay, we don't need to do a calculation to determine the terminal voltages. They're already given to us. VB, voltage at the base, is given as 2 volts. So V1 is 2 volts. Voltage at the emitter is given as 1.3 volts. And voltage at the collector is given as 4 volts. So the first step is to determine whether the base emitter junction is forward bias. VBE is VB minus VE. It's 2 minus 1.3. So it's only 0.7 volts. Forward bias or reverse bias? Shouldn't take this long. It's forward bias. Forward bias PN junction. It's 0.6 to 0.7 volts. That means it's on. And it's an NPN transistor. If this was a PNP transistor, then it should be minus 0.7. And because it's 0.7, therefore, it's not cut off. It's not cut off. Right? That's always the first step. Check the base emitter junction. If base emitter junction is reverse bias, transistor is off. No need to do anything else anymore. But if it is forward bias, then it means it could be active or saturation. Okay, active or saturation. And in order to test for that, we need to determine VBC. Again, VBC. Base is positive or P-type. Collector is N-type. So base must be higher than the collector. So VBC must be positive. So 2 minus 4, and VBC is negative. So what does it mean? Is the junction forward bias or reverse bias? If it's reverse bias, then is it in saturation or active? It's in active mode. Active mode, yes. Everything's, yeah, if it's PNP, then everything is switched, yes. So the question being asked is, why did we ignore? We actually didn't ignore, we just, well, actually we did ignore, but the only reason we would need to use those is if we want to calculate the voltage at the base collector and emitter, but they're already provided to us. That's why I like to use this example as like a first step. So the voltages are already provided, the terminal voltages at the base collector and emitter are already given to us, so we don't need to calculate anything else. We're simply observing the voltages and determining the operating mode. There's one more test we can perform for saturation. So in saturation, VCE, collector emitter voltage, is typically 0.2 volts or less. Okay. Remember the characteristics right here. Saturation is this region on the left, right? Because current saturates at a limit. So voltage, which is on the x-axis, is closer to the origin. It's close to 0 volts. So VCE, collector emitter voltage, if it's 0.2 volts or less, then the transistor is in saturation. So that's the other check we can perform. And in this case, VCE is 4 minus 1.3. It's 2.7 volts. So it is not 0.2 volts or less. It's far larger than 0.2 volts. Therefore, not in saturation. Okay. Two alternative methods to determine whether it's an active or saturation. All right, questions? Do the steps make sense? Okay, so this is where we had to stop in the previous class, and I guess we are almost out of time, 20 seconds left. So I'm gonna end class here today and pick up here again on Wednesday.